So basically now we have C RLC measurement and voltage and current measurement. Okay. This is using bridge. This is using Diasono setup. Diasono setup. Okay. So you should focus on these two. Okay. Some question will come to the exam uh, with these things. Okay. Okay. Now we also have to measure signal. Okay. We also have to measure signal. Okay. So I think maybe Udayanga, can you remember what is a signal? Okay. Actually, signal is any parameter, any physical parameter, physical quantity. Okay. That is varying with another physical quantity. That is a signal. Okay. For example, one physical quantity may be temperature. Other physical quantity may be pressure. Okay. So when the temperature is increasing, maybe the pressure is increasing. That is happening in air. No? Okay. PV equal nRT. When the temperature is high, the pressure will be high. Okay. So this temperature is one parameter. This P is another parameter. Okay. That is a signal. Okay. But but uh, but we are in electrical domain, electronics domain. Okay. So most probably we consider signal as voltage, current, or power. Okay. Power is actually VI. Okay. That is again voltage and current. Okay. So these are we considered as signal, voltage signal, current signal, and power signal. Okay. So this voltage signal means the voltage is changing with time, most probably time. Okay. Okay. The current is changing with time. Time is also a physical quantity, and voltage and current are also physical quantity. Okay. So time, voltage varying with time, current varying with time, those are electrical signal. Okay, those are electrical signal. Okay. For example, if you consider AC voltage, okay, sinusoidal voltage, it is changing like this with respect to time. Okay. So this is the signal. This is a signal. This is a signal. Okay. Okay. Now signals are not only time-based signal. Okay. Here the independent variable is time. Okay. Okay. It is in time domain. Okay. So we call this time domain signal. We call this time domain signal because because the the domain is time, the independent variable is time. Okay, so we called it time domain signal. Okay, okay then. So this is a time domain signal. Why it is time domain? The independent variable is time. The signal is changing with respect to time. So this is a time domain signal. This is a time domain signal. This is a time domain signal. Okay, and uh, maybe then maybe have you done DSP, digital signal processing,
Uh, Not yet.
or signal and system?
Signal and systems I'm following. Yes.
Yeah. Okay. So maybe you can remember that we have learned some some very important technique that is called Fourier analysis. Fourier analysis. Okay.
Yes.
So this Fourier analysis to find we use to find Fourier analysis we use to find the frequency component of a time signal, of a time of a signal. Okay. So in other words, for example, using Fourier transform, we convert time domain signal. We convert time domain signal using Fourier transform. We convert time domain signal into frequency domain signal. This independent variable is t. Here, the independent variable is frequency. And using inverse Fourier transform, we do the other things. here in this, okay, here the frequency domain signal is converted to again time. Okay. Okay. So in frequency domain, we plot the voltage of power with respect to frequency. Okay. This is frequency. This is frequency. Okay. So when we are analyzing signal, when we are measuring signal, we have to mainly measure the signals in time domain and frequency domain. Okay, so that is very important. Time domain signal we normally called as waveform. Frequency domain signal we normally called as what? Can you remember? That is normally called as spectrum. Okay, waveform and spectrum. Okay, so signals you should be able to measure the waveform, and with respect to signal, you should be able to measure the spectrum also. Okay? So what is the instrument we measure the waveform? That is oscilloscope. Okay. To see the spectrum, there is another one, that is spectrum analyzer. Okay. So these are some tools, some equipment, just like voltmeter. Okay. So I think you are familiar with oscilloscope. Maybe as a power student, maybe you haven't used spectrum analyzer, but in power domain also spectrum analyzer sometimes used to measure the spike. Okay. To measure the spike, to measure the interference. Spectrum analyzer is used in power domain also. Okay. So what I want to tell you is that if you consider a signal, there are two form. One is time domain and one is frequency domain. Time domain we normally refer to as waveform. Frequency domain we normally hello. Okay. Okay. Time domain we normally refer to as waveform. Frequency domain we normally refer to as spectrum. And you need to check waveform using oscilloscope. You need to check the spectrum using spectrum analysis. Okay. Now, one thing. Okay. So if you consider sinusoidal signal time domain is like this. Xt is equal to A C cos 2 phi FCT plus phi. This is the normal time domain sinusoidal signal. This can be cos or sine. Okay, this can be cos or sine. Okay, so Udayanga, you need to, maybe you are not expert in signals. Okay, because you are in power domain and almost you may have forgot the signal and system. Okay, but you have to refresh this memory. Okay. Okay, so so this is a time domain signal. Okay, it's a time domain signal. Oh, මොකද කරන්නේ? So this can be also sine. Okay. So this AC, maybe you can remember that here no AC. Okay. Okay. Here it is just A. This is amplitude. This FC. This is no need to write FC. Okay. Actually, I just do the communication system lecture. Okay. So that is related with the amplitude modulation. Okay. So carrier signal is there. Okay. So for the carrier signal, I use FC and AC. Okay. So that is mistake. Okay. Here it is just F. Okay. What is this F? It is frequency. This is measured in normally volt or current. If it is a current signal, it is amplitude. If it is a power signal, it is watt. Okay. So normally measured in volt. Okay. Normally measured in volt amplitude. Frequency measured in hertz. Okay. And what is this? This is a phase. This is a phase. Phase is measured in radian or degree. Most probably radians. Okay. So these are the three parameters related with amplitude, frequency, and phase. Okay. And also this F, also we can write as 2 pi omega. Sorry. Omega you can write as 2 pi F. Okay. This is normal frequency measured in hertz. This is we called angular frequency. Actually, this is angular velocity. But angular frequency is also correct. Angular frequency. It is measured in radian per second. Okay. And maybe you know that F is equal to 1 over T. This T is a cycle, one cycle. Okay. For example, if I give you like this, okay. Maybe you will have to draw a simple signal like this, okay. Maybe in your exam, this kind of simple, you have to draw this kind of simple waveform, okay. So so if I give you like this, okay. So let's say that you have a sinusoidal signal, sine signal, okay, sine signal. Amplitude is 2 volt, frequency is 100 hertz, and phase is 0, like this. Okay, phase is 0. Okay, so how you can write it? So sinusoidal signal means it is definitely like this. This is called one circle. This is called one circle. Okay. Number of circles per second is normally referred as frequency, F. Okay. So that is number of circles per 1 second. Okay. That is the number of circle per 1 second. Number of circle, F for 1 second. Okay. And if you want to find the time for one circle, that is 1 over F. This is time for one circle. This is time for one circle. One circle. That is referred as period. Period. Okay. So you can get T period as 1 over F. That is the time for one period, one circle. One circle. Okay. So what is the period here? So this is one circle. This is one circle. Okay. So one circle time is this one. This is one circle time. Okay. So how you find the one circle time? So you have the frequency, that is the number of turns, number of circle for 1 second. Then for one circle, the time will be 1 over 100. Okay, that is 1 over T. That is equal to F. Okay. So, sorry, 1 over F, that is equal to T. Okay, because 1 over T is equal to F, that means F is equal to, sorry, T is equal to 1 over F. Okay. Okay. So this is the period, one cycle time. So this will be 100 seconds. Okay. Then this is a half cycle. That means half of this. That means 1 over 200. This is double. That is 200. Okay. This is 1.5. That is 1.5 of 100 seconds. Okay. Likewise, you can find this time value. You can find this time value. Then the amplitude is 2. Amplitude means peak value, this value. Phase is 0. Okay, phase 0 means you are starting from here. See, if this is 90, you are starting from here. Okay, if this is 180, you are you are starting from here. Okay. So that is how you can draw a sinusoidal signal. Okay. So maybe this also may be somewhat important, but here we have time to draw several signal. Okay. So try to draw this kind of signal. Okay. So if I give you xt is equal to 2 cos 2500 t plus 90, try to draw this one. Okay. Then this one next to t 2 cos 25 300 t plus 180, this kind of circle. Then it's 3t maybe 5 cos 300 t plus 300 t. Okay. So try to draw these three signal as a homework. Okay. Try to draw these signal, three signal. Okay. So try to do. Okay. So if you have any problem, please ask me. Okay. So maybe you can draw this and you can send me through WhatsApp. Then I can check it and tell you whether it is correct or not. Okay. So try to draw this. Okay. Or if you can use MATLAB. Okay. You can just draw this by hand and using MATLAB, you can verify whether you draw it correct or not. Okay. So try to do this. Okay. Now another point. Okay. Now another point. Okay. So this is the waveform. Okay. So I draw this with respect to time. This xt with respect to time. This is the waveform. This is a waveform or time dimension. This is a waveform or time dimension. Okay. So if you send this signal to oscilloscope, the oscilloscope will be showing this kind of signal. The exact this signal. Oscilloscope will show this signal. Okay. Waveform. Okay. Okay. Now, if you consider a sinusoidal signal, as I told you, xt a cos 25 ft plus 5, this kind of signal, this f is the frequency. I told you first, frequency. That is the only frequency this signal has. Okay, that is the only frequency this signal has. So this signal is one frequency component. This signal is a one frequency component. Single frequency. This is normally called as tone. This is a one tone signal. This is a one frequency component. Okay, only one frequency is there. Okay, so if you consider that signal, again I will consider this one, 2 cos 25 100 t plus 5, 100 t plus 90, this kind of signal. Okay, what is the frequency of this signal? That is f, this one, 100. Okay, this is the only frequency. This is the only frequency. Okay, so if you draw now, if you draw the voltage with respect to time, you will get this kind of. Okay, if you consider this one, if you draw the voltage with respect to frequency of this signal, what type of signal you will get? You will have only one frequency. The frequency is 100. What is the amplitude? That is 2. Okay. So this kind of signal you will see. Okay. Okay. So if you see this using oscilloscope, you will see this kind of one. If you see this signal, sinusoidal signal through a spectrum analyzer, you will see this kind of one. Okay. If you use oscilloscope, you will see this kind of one. Spectrum analyzer, you will see this kind of. Okay.
Okay.
Did you get it?
Yeah.
Okay.
In the
Actually,
spectrum
spectrum analyzer
only the
will show this
frequency.
kind of one. This kind of peak you will get. Okay. So here 2 volt. Okay. Actually, spectrum analyzer will not show this 2 volt. Okay. but actually spectrum analyzer will show the power. Normally we can have the power spectrum, not the voltage spectrum. Power spectrum from spectrum analyzer, okay? So how to calculate the power of this sinusoidal signal? Power of the sinusoidal signal will be A square divided by 2. Amplitude is square divided by 2. So here amplitude is 2. 2 square divided by 2 means 2 watt. Okay. So normally you will get this power 2 watt. Okay. Actually this is in dB. Normally spectrum analyzer will show this power level in dB. Okay. So this kind of signal you will get. You will see. Okay. Now, if I ask you this kind of, if you are given this kind of signal, 2 cos 2500t plus 3 cos 200t plus 5. This kind of signal, if I send this kind of signal, okay? So you can draw this signal in time domain. Okay, you can draw this signal also in time domain. Okay, then this signal is a DC signal, DC component. So it will be like this. Okay, this is time. This is voltage. Okay. So this signal means DC signal. That means constant voltage, DC value. Okay, DC value. So you will have this kind of 3 waveform. To get the resultant waveform, you have to add, because all signals are added. You have to add them. Then you can draw the signal. Okay, so that is very hard. Okay, so definitely you, for the exam, you will not get this kind of question. To draw the waveform of this circuit, of this signal, definitely you will not. Okay, so you can send this signal to oscilloscope. You can check this. Okay, and also you can code this in MATLAB very easy. And using MATLAB also you can view the signal. But if you draw by hand, it will be not easy, because this signal you can draw, this signal you can draw, no problem. This signal also you can draw, but you have to add them together. So that will be very complex. Adding will be very complex. You have to get point by point, okay, to add. Okay. So you will not ask to draw the waveform of this kind of signal. This is we normally called as composite signal. Okay. So you will not ask to draw the composite signal waveform. Okay. But if I ask you to draw the spectrum analyzer, that means if you send this through the spectrum analyzer, what kind of signal you can see? What type of signal maybe you can see? Can you think? Okay. So now if we send this signal through a spectrum analyzer will show us the signal in frequency domain. Okay. So how many frequencies are there? This is one frequency. This is another frequency. For DC signal, there is no frequency. Frequency is 0. Okay. So 0 frequency is there. Okay. So 100 is there. 200 is there. Okay. 200 is there. Okay. So here, this is not a frequency component. Okay. So no value will be shown for this one. In this 0, there is no any peak. Okay. Because there is no frequency. Okay. But here we have a frequency. Here we have a frequency. This power is 2 square divided by 2. That is 2. This will be 3 square divided by 2. That is 4.5. So spectrum analyzer will show you this kind of signal. Okay. So did you get this, Udayang?
Yes, sir.
මේක තේරුණානේ? හරි ලේසියි. Frequency component ටික බැලුවා power එක අම්මා. එච්චරයි. Okay. So that is it. Okay. So if I give you this kind of signal, 5 cos 2500 t. So maybe this kind of signal you should be able to draw the waveform and spectrum. waveform and spectrum. Okay. And you can maybe you can try to draw this spectrum to 500 T plus cos 300 T plus sine 200 T. Okay. So try to find this one spectrum also. Only spectrum also. Spectrum. This one waveform and spectrum. Okay. So try to draw this. Okay. So once you calculate the frequency, okay, so this is 300, okay. Actually 300 is equal to 25F, okay. To find F, you need to divide 300 divided by 25. Likewise, you can find 5, okay. If you are given like this, you have to use this equation, okay, to find F. When finding F, you can find the T, then finding T, you can draw the signal, okay. So here also you have to do that, like this, okay. In this case, you have to find the T using, this is actually omega, okay? This is omega. This omega is given 25F. Omega is equal to 5F, no? I told you, okay? This total term is omega. Okay, this. Okay, so don't get confused. Some small, very simple things is there. Okay. Okay.
Okay.
Udayanga, did you get it?
Yes, sir. Mostly good.
So if you have any problem, you can ask me. Okay. So wait for a moment. So wait for a moment. We will stop now. Okay. We will stop now, but wait for a moment to get the